All right, I'll try to amuse you today. So, all right. Okay, so there's a little bit left that I wanted to talk about with this is system robustness. That's where we're going to go, right? We've done all this power law business, and here's another world of power laws, right? Things that explode, the statistics of surprise. So we want to look at why this is another kind of mechanism, very plausible kind of mechanism. It's very, well, it's contested and so on, but it's got a lot of press for itself. This is the highly optimized tolerance thing. So lots of fun stuff there. It's an evolutionary kind of engineering type story, which is, cool. And okay, so just to start with, I want to finish this little piece here on statistical mechanics. So I'll give you a simple little question about percolation. You guys can work on that. Maybe some more. It's good stuff. It's good, nutritious physics and thinking. Yeah, very nutritious. All right, so this is the sort of thing that comes. I mean, there are many, many plots I could put up. I'm putting up physical systems, but there are all sorts of examples. This is the classic kind of thing for fluids, right? So depending on temperature and pressure, you get qualitatively distinct types of macro states, right? It's a fluid, and it could be a fluid with different types of temperatures and pressures, but there's a transition as you cross here, now we're into gases, now we're into ice. So that's or whatever it is, a frozen state. So that's the big deal, right? So we have these changes, these small detailed changes, and we get these massive, macro transitions, right? So you see that sort of thing in all sorts of examples. Traffic, for example, you can talk about, the speeds of cars and so on, and see when you get to jamming states. Many, many things. Dynamical systems are full of this, right? So here's a fun example from a while ago, 1996, and it's actually the classic example. This is Michael Faraday set all this stuff up, right? So shaking liquids up and down in a tray. So I did this over and over again, and it's good. Actually, I have a photocopy of his paper from like 18 whatever. It's fantastic, and just daily going in and shaking in different ways, different amplitudes, and getting patterns that look like hexagons, so like a beehive sort of thing, or a bee honeycomb. Or lattices, square lattices, like these different things. So granular media remains this very difficult field, right? I mean, in terms of complex, phenomena, it's really complicated. Fluids are very difficult already, but we at least have the equations, and we can go out and model things. Granular media is sort of fluid-like sometimes not, right? So there are classic and quite disastrous problems. So for instance, a silo, right, if you fill this up with grain, and coming from a farm, I guess I know some of this, but you fill it up with if you fill it up with liquid, then the pressure on the bottom would just increase linearly, right? It would just as you added more. And so all the stress would be down here. The stress that would be adding onto the sides would be, the same as you keep going up. But you get this thing in granular media, and so this is stuff that was figured out in the 90s and keeps going, lots of work. Force chains, right? So the way that the force is being distributed through granular type things, so say, wheat and grains, is not uniform at all. It's very complicated and messy. And so a lot of it gets pushed onto the edges, and that's, in fact, you get exploding silos because of this. It's a very sort of odd thing. And you can, for instance, let out some of the grain or whatever it is at the bottom and get caves, right? You would never get that with liquid. And very incredibly dangerous, right? They collapse on people and so on. And now, granular media, it's huge, right? Food. I mean, just as we're talking about wheat and rice, and I mean, we're moving granular stuff around all the time. And right, if you've ever tried to get your whatever it is, granola, because we're in Burlington, out of a box, and it doesn't, right? I mean, writ large, that's a big problem. For you, it's a small stress in your morning, and you're probably thinking that's as bad as it gets, but it gets worse. Okay, so this is granular media, very interesting. So. Umbenhauer and Swinney, this is down in Texas, they did some work where they said, all right, well, let's put a bunch of ball bearings on a plate and shake it up and down. And so they got some really fun things. One was these oscillons. So they're isolated little waves. And here's a couple of examples. They just go bloop, 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 bloop. And they're not connected to anything else, which is very unfluid-like, right? You can actually produce this in fluid. Some mad people managed to do that. But again, one of these phase diagrams, right? So this is the frequency, this is the amplitude of the shaking. And so you get qualitatively different things, squares and these so-called oscillons, which made the front cover of Nature, which was pretty cool. Flat layer, that's where you would put them if you found some oscillons on the front cover of Nature. Wow, that's an old joke. Stripes, all sorts of other things. Another example, I mean, there are things like this, right? Snowflakes, This is actually bacterial growth, right? So depending on nutrient amounts and so on and other things, right, you get these qualitatively different things. So this is definitely not fractal shaped, and this is, and so on. So, right, this is something you might look for in systems where there's a transition between, you know, society staying together, falling apart. And another, so I'm just touching on these things. One other sort of very perhaps surprising piece about statistical mechanics is that the 1D problems are usually very easy, right? So we talked about these magnets, right? These little spins. You can solve it, right? So you can just solve that problem. Percolation, you can solve it, and that'll be a problem for you to work on. 2D turns out to be really hard, and it's usually, if you do this, you're a hero in applied math or physics, right? You've done something really ridiculous. You know, many monks sort of situation, right? And the path is not clear at all. So this 2D Ising model was solved actually in 44. 3D, as I understand, has never been solved. And 4D and up, and maybe I have this wrong for the Ising model, but 4D, usually 5, there's some so-called upper critical dimension, after which everything is basically mean field, which means that everything looks like it's just a big random mixing mess, which you can solve easily. So if everything's randomly mixing, you know, analytically, it's easy to work with. So you get this odd thing. This is, of course, where we live, right? In 3D and 2D. We're very 2D when you look at us from space, right? The way we kind of run around on the Earth. And there's a lot of 3D locally. But these are where we are, and so it makes things hard. That's a bit surprising. You'd think, you know, 17 dimensions should be just crazily hard, but not true. Actually, it's really easy. Last piece that I wanted to add in all of this was that StatMech, and maybe I said this, has this kind of weird origin in that it came from physicists thinking about how people were thinking about people, right? So we were getting this statistical kind of actuarial type tables about how many people are going to die falling off a horse this year and how many people are going to, you know, do certain things. And some people were very upset, right? Because it sounds like it's something against God, perhaps, right? Randomness and unpredictability. But that was being used to describe behavior of people. And so this is a world of mechanism, right? It's statistical mechanics, right? Mechanics should not be statistical. It's mechanics. It should be, you know, you push this thing and this thing moves, and you push this thing and this thing moves, right? So they did this crazy thing of saying, well, let's let these little, whatever they are, molecules and so on, behave statistically, and we'll build up from there. So then the odd thing is that you have physicists rampaging out of StatMech, which has had 100 years of, you know, doing a good job, and saying, let's apply it to people. People are magnets, you know, so. So you get people thinking they'll do everything with it. There's a nice Philip Ball's critical mass, which is, you know, now moving into the past. I guess it's 2004 or 5. Has some very nice pieces about this. All right, so that's just to give you a little bit of the history of how that works. All right, so I have some videos in the next one because, of course, partly because I figured out how to put videos into Beamer. So I apologize for that, but I think it's thematically sound, so we'll see how that goes. I'll probably get sued by someone. Yay. All right, so system robustness. So this is a really interesting piece. Okay, so this is going to be something we'll figure out what this is, but it's something to do with forest fires and setting up optimal breaks. Do a little thinking about this. All right. So hot theories first. There will be this narrative causality. That's just a side piece. Right, so you know if there's a 1 in a million chance of something happening, then it happens, right, in a story. That's important. Yeah. It's like 1 in 100,000, that's not enough. Like it has to be 1 in a million. It's 1 in 10, then clearly that's not going to work either. So very strange things. I mean, the stories we tell, right? Anyway, so all right, so we'll have that. That will somehow tie into this. Not really. We'll have cold theory, which is, you know, everyone is funny, so they make their, you know, their acronym go against hot theory, but actually they're very adjacent. And then we'll talk about this big deal, self-organized criticality. It's a huge deal in the 90s and still going on. People will talk about it in this way. Those words are very powerful, but we'll see, so SOC, right? So this is SOC. We'll see these things match up in very different ways, right? SOC and hot. So there's a big contest between SOC and hot. And then cold is like a little friend of hot, even though it shouldn't be. And then a little bit piece about network robustness. And then we're into complex networks anyway, so that's a nice tie. Okay, good. So there are so many, this is, famously the story we're in now, right? Many systems, and of course natural systems, we've seen this forever, whatever it is, volcanoes and hurricanes and all sorts of things exploding. That's happened forever, and we tell stories about it. Floods. So blackouts, of course, is a thing because we've created this monster smart grid, or this monster grid, and we're trying to make it smart, but we made kind of basically a big dopey grid science, by connecting what were locally pretty smart structures and into this big thing that made sense business-wise, and so there's money flowing around as well as electrons, and you didn't have an engineer laying the whole thing down, right? So you see some funny things like that at all scales, like the New York subway system had competing subway companies, so it ends up with a bit of a funny structure and some kind of dead lines as well that are just sitting underground. So, and sometimes that works well, right? There was a paper a few years ago where they got slime mold to produce the Tokyo subway system by letting it grow and putting food at the various stops, and it produced the same network structure. So, okay. There are some silly things that we do. Okay, disease outbreaks, right? So things are going okay. Of course, there's disease everywhere all the time. Sometimes, boom, it kind of takes off. Wildfires, and we, now we kind of understand that we do some bad things with this by, not by preventing little fires and, producing huge ones. Earthquakes, we're not really in control of these guys at all, and prediction is a huge problem. That's what we want, right? So we want to predict all of these things. Right? We just talked about in reading group yesterday, predicting social contagion. Love it. If we can do it. Didn't work? Okay. Now, of course, these are the things we focus on, right? So if you think about movies and planes in movies, this is terrible. Look, sunlight. If you think about, it'd be kind of an interesting exercise to get all the footage of, obviously a tedious one, footage of planes, right, that appear in movies. They must, the amount of time that they're in jeopardy, right, per unit time on screen must be ridiculous compared to what happens normally, right? We fly around all over the place and nothing happens, pretty much all the time. But we're kind of terrified because, you see these images of things exploding all the time, right? Yeah, right. So, get a bit of a warped idea about that. But the truth of the matter is, a lot of things hold together, right? And that's why they're still here, right? So, we are these funny, complex systems. We get out of bed every morning and bad things happen to us, but we persist pretty well, right? Things like a heart beating for 80 years is insane. That's a crazy thing. You engineers should build one of those, right? It's not as exciting, of course, because, right, that doesn't make for good movies, so we don't talk about it. It would be really a terrible story, right? Writing about how many hours. It'd be actually kind of a nice little footnote. We had 4 bazillion hours of flights today and nothing happened. It's just X sat on a plane and nothing happened, and they played with their iPad and nothing happened.
Is this version of robustness like the traditional math definition of robust, or are we kind of defining something else now that we're talking about complex systems?
I don't know if there's a traditional math. It's more, this is just, does the thing explode or not? Is kind of the key issue. Is that?
How far do you have to?
So you have to quantify what the damage, right? So depending on the model you come up with or the thing you're really studying, you probably have to create a measure of damage, and it could be money, it could be hours lost, it could be, right, all these things, and you probably need a whole page of diagrams, things you care about.
Measure of damage that you
ability to recover.
Right. So we have this is aside, but we have a paper from 2003, it was in PNAS about, it was exactly this, it was about organizational structures, right? So hierarchical structures are sort of underneath many organizations. And they're the kind of things that you produce when you know exactly what you're doing, right? You have this clear reporting structure. But they're not very good they're brittle, right? If it's a pure hierarchy and you take out the top layer, then the whole thing is disconnected. So you add crosslinks and so on, and if you do that in the right kind of way, you can make these structures that are resistant to damage, and even if they are damaged somewhat, they can still communicate, right? So they hold together. So there's ultra robustness was this absurd term we came up with. Okay, anyway, it's a little much, isn't it? Yeah. That's why my brain has forgotten it. All right, so, okay. So this may be a power law story, okay? Again, the statistics of surprise, things go boom, we'll see. So here's a good emblem, and we'll use this throughout the, right? Very robust, but an absurd plot device means that it can explode, okay? So, right? I mean, there are a lot of places to drop that little missile in, and just one, yeah. All of the other ones, no, it doesn't work.
Wait, cover that was up before.
What's that?
They just had that one person who needed to cover up that one, but needed to fix that.
Yeah, right. So we'll have some comments on that, actually, from some of the people involved will have comments about this.
It's an Imperial fighter.
Sure is leaving in a big hurry. If they identify us, we're in big trouble. Look at him, he's heading for that small moon.
That's no moon. It's a space station.
Caught in a tractor beam that's pulling us in.
Okay, so that's it. All right, there's a little setup.
What did you label on the Death Star?
Oh, I just snared that from somewhere. That's, I think it's from Wikipedia. And it's, yeah, oh, sure. You can get exploded technical diagrams of anything. Daleks, for example.
Yes.
Yeah. There was one at a museum that we went to, and Sophie was thrilled by the exploded Dalek diagram, which someone had very, very nicely drawn, put together in 1965 or something. Very careful. What was this? This is the Museum of London. The Museum of London. So just around the corner, for example, was a map that the Germans had drawn up that said these are the places to bomb, and it's incredibly detailed with like keys and legends. It was a complicated museum. So around, Daleks here, and the Blitz is around the corner, a little confusing. I think they were just trying to take the edge off it. Right, weird. Okay, so how do we get this robust? So we're going to have a few more of those little pieces, and it will get more and more ridiculous. Okay, so, Star Wars is already absurd. So let's see. So evolution and engineering, right? These two driving mechanisms of building more and more complex structures that we could talk about here. And, both of them, once we get up to certainly large enough engineering systems, there's going to be some effort to quantify the uncertainty, right? And that can happen naturally through evolution, right? You understand you might get eaten, so you behave in certain ways, and this can go spectacularly wrong. But this is the idea. We somehow have to characterize the unknowns a little bit, right? So this is the known unknowns. Yeah, the unknown unknowns are really bad. Yeah. I know there's a bit of flack about that whole story, but that is really a very reasonable thing to talk about. The unknown unknowns. You got to watch those. The known unknowns are your left null space for linear algebra fans out there. Okay, so highly optimized tolerance. Hot. So this is a very important part of this was the branding. And then there's two terms here, robust yet fragile, right? So we've got the hot model and this kind of flavor of systems that we see over and over again. So Gene Carlson, who's at Santa Barbara, I think I mentioned this, John Doyle, who is very much worth looking up. Okay, so great abstracts of the world. This is one of them. Let me show you this. You saw what it was, but okay, here it is. Guaranteed margins for LQG regulators. Abstract, there are none. Okay. There's one recently with that whole, the neutrinos going faster than the speed of light, which had some, kind of question mark title, and then the abstract was maybe. Yeah. So, good work, humans.
Who's willing to supply that?
I don't know, but that was his first published paper, actually, so that was pretty solid. I mean, okay, so this guy is a bit of a character, yeah.
Well, it should be a lot.
Well, there's definitely a lot to be put in your title being a good title, and you see it goes like, there are things that my theory predicts right? There are terrible titles, right? Which you're disappointed when you go in. Yeah. It's like a trailer for a movie. But if it's if it's well done, so he has this his little web page here which talks about excellent things he has done, right? So he's about to turn 60 for him to tell. Here are the stats right up. And he's got some good stuff here. Look, he won all these races back in the day, and he could knock out 54 minutes for a 40K bike time trial. So pretty solid. Just so you know, pictures.
36 minutes.
Yeah? So this is the man we're dealing with here. Pretty funny. Yeah, very funny guy. Anyway, so yeah, okay. This is the idea coming out of a bunch of papers, but this is what they want to see in systems, right? They perform well, right? The thing keeps going and has a robustness to it, so it doesn't. It performs well what it's supposed to do, but it also doesn't, break apart. So that's often the performing very well, you can end up with a bit of a brittle system, right? Because it can be just too well-defined, well-structured. And then as soon as some change in the environment comes along, you can't adapt. All right, so there has to be some kind of way of characterizing uncertainty in the environment. But then if there's a really big change in the environment, right, statistically speaking, things happen in a very different kind of way repeatedly, it could explode. I'll repeat these things, but what you tend to find is that you get systems that have, or structures that have this kind of very specialized so-called low entropy structure to them, right? So they're very, they're things that can't be built randomly, right? And so there are a number of kinds of systems that are random in nature. This SOC, the self-organized criticality, will come to, that don't really have structure in them, produce power laws, but in a very, very special way. And of course we get power laws, right? So this is a bit of a hard thing to do, as I was just trying to touch on, right? Usually in StatMech, power laws come out of structures that actually are there's a lot of randomness in them. But so these are going to be very particular structures, all right? So there are a couple of things. So we had this variable transformation story, right? It was a very simple thing, but we took nice looking distributions, exponentials, Gaussians, and so on, had a transformation that involved a power law relationship, and it ended up with power law size distribution. So that was a very plausible sort of thing. There's going to be so there's this piece, so it's just very natural, and there's going to be some sort of constrained optimization, right? So there's going to be some cost associated with defending yourself against the environment, which limits the way you can do things, giving rise to certain kinds of structures. Kind of the idea. There's a very geometric feel to this, and the example we'll go through, the forest fire one, is extremely, it's just patently geometric. All right, so this is this transformation, the variable thing. Pleplo is bad, right? Mild in, wild out, that's all good. So we've talked about these things. So there'll be X, this guy has some characteristic size, but Y does not. Fair enough, all good, fine. So we'll see that come out. So here's an example. This is actually a bit of a hard thing to code up. I want you to try and do it in 1D. It'd be nice to do it in, if we're really keen, we can do it in however many. You can do it in 5 to me. No, we should do it. We should do it. See if we can do it in 1D, and 2D would be great. 2D would be great. I mean, they did it with I'll show you a pretty small example. And maybe I haven't looked around properly. There should be a functioning version of this somewhere, because it is the great example for their work. So, all right, so we're going to have an n by n grid, and then we're going to put down trees with probably, with some density rho. Okay. And if it's just we'll talk about how we put these things together. Okay, so there's going to be some density of trees, and okay, so the very simple thing is, incredibly simple forest fire model. If you've got a tree here, and you've got a tree here, and there's just gaps here, gaps here, gaps here, and maybe it looks like this, right? And there's a tree over here. These are all gaps, so nothing here, right? So this one gets on fire, then the next time step, this one's on fire, and this one's on fire, because they're adjacent, but nothing can spread out past that because of these blocked things. So pretty simple.
Is it your 8-person neighborhood or your?
Yeah, so just 4, I think, in this one. Yeah. All right. Yeah, which can matter horribly. Yeah. Yeah, 4 in this one. Yeah. It matters. The type of grid matters. So that's a bit of a thing. But really, we should simulate a lot more things on hexagonal grids, but they're just a little bit sneaky. I'll come to that later on in the course. There's a real reason for that. What's that?
You can repeat it.
just.
You'd store it as a matrix, but you'd have to, have some little things about how you,
Okay, but
triangular lattice, hexagonal lattice. They just have some very nice, they have very, very special properties. It's the only lattice in 2D that has a certain list of special properties. We'll come to it much later on. There are none in 3D, and there's one in 4D. So if you want to do it in 3D, you have to project the 4D. It's great. Okay. So tree to tree, nearest neighbor only. So basically, yeah, as soon you don't have to run the simulation. As soon as a cluster gets hit, then boom, it's gone, right? So then you can start to think about, all right, well, what are the distribution of cluster sizes? And if one of them gets hit randomly or according to some distribution of these sparks, then what happens? All right. So this is what you're trying to do. You're allowed to build fire breaks. You've got to maintain them. You have a certain amount of energy, a certain amount of cost and money or whatever it is. So you have to keep putting them in there. Making sure they hold up. You can imagine there's an initial cost and so on, but basically we'll just talk about sort of a maintenance cost. So how do you put down your fire breaks given some distribution of, it's not not a uniform distribution, a somewhat uneven distribution of sparks, so that on average the forest holds up the best, right? Okay. So here's a kind of a, this is a toy model. This is sort of an engineering, it's very much a toy model, right? This mechanism is barely a mechanism, but it's there. Okay. So we're going to build our forest in a very odd way. We're going to add one tree at a time. So you start with a blank space, and n by n, and then you have D tests you can do, right? And so D is the design parameter. So if there's only one test, so you put your tree down and then you let some sparks go, according to whatever the spark distribution is, and then measure how much forest is left. So to start with, obviously if it hits a tree, you lose one, but basically to start with, you're going to miss those guys. And it'll be very sparse to start with. The forest is going to be quite sparse. So as you fill it in, eventually you get to some point, which is this percolation story, where there's actually a really big forest, right? And that becomes prone, dangerous. If D equals 1, and I'll say this again, yeah, here it is. So you average over the spark probability, right? You run the thing again and again. D equals 1 is basically random addition, because you can't test. I mean, you let it run and you just look at what happened, but you don't get to choose different locations. D equals 2, at least you put down this tree, and then maybe you put down this tree over here. You test both of them, and you take the best one. So that's, right? So that's a jump. N squared means you test everything. So that's extreme and computationally pretty hard. Okay. So you measure if you like, the yield. Well, first of all, there's a forest fire size, right? So that's going to be your cost. So you find the distribution of that. And the yield will be whatever your density was to start with minus the average forest size, right? So if you start with half, if the density is, say, a half, and a quarter of the space gets burnt, meaning, okay, that's complicated because your average forest size is a quarter of the whole n squared, then, right? So a half minus a quarter, your yield is a quarter. Fair enough? Okay, so here's, I'm going through this one particular piece that they put out. So we're just going to have a simple, okay, so this is part of some bigger grid. I is measured this way, say, and J this way, and we're going to have simply a probability distribution Pij, which equals Pi times Pj, so it's just a simple product. They're independent of each other. And we'll have both of them decay according to some, like it's part of a Gaussian, right? So if you looked at it this side, you'd see it's going to be P plus A, that's true, right? So it's going to die away as a Gaussian here and as a Gaussian here, right? So these, if you look at the spark distribution this way and the spark distribution, you have the product of them, and one of them dies way faster than the other.
This is spark distribution, not tree distribution?
Right, so the tree distribution you're trying to build on top of this uncertainty. So the uncertainty in this case is, it's pretty extreme. So if you're down in this, corner, it's pretty close to 0 for the spark density. It depends on this A, it depends on N, and so on. But the idea is it decays. So it's bad in this about over here, right? But there's an asymmetry to it, so it's sort of maybe more like this, right? Or the other way. Is that? Yeah? Yeah? All right. Okay, so in the original work, we actually had this, right? So there's more width in the y direction. Yeah. Okay, this direction. Right, so this one sort of comes down steeper, this distribution. So it's a Gaussian, it's decaying as e to the minus x squared, which is very fast. This one's a bit further. All right, so let's try to understand these outputs. So this is using a design parameter of 1. We're going to spend some time on this one. Design parameter of 2. And n and n squared. All right, so it's not a huge grid. I think it was, so 64 by 64. Obviously, we could be enticed into doing monster ones now, I suppose. But this is, the first papers here are 99, I think. Yeah. Okay, so this is the random one. So you're just randomly putting trees down, and trees are white. Okay, so the blank space, the black means there's no tree. So there's an A in here, so I can't really tell. If you started your fire here, then it's going to burn, and it actually would get around this corner and get all of this. Actually, it's pretty bad. It would get all of this stuff as well, right? So that would all go boom. And if it lands in any of those, and if it lands, of course, in a blank space, nothing happens. So this is an example of the best forest that random design can produce. This is just at the cusp of creating a super forest, right? So as I showed you this funny little bit here that connects, you just add a few more trees in here and then all of this will be connected, very thinly, but it will be connected. So this is this percolation structure. As you randomly add trees, you go from having trees all being isolated to having some clumps to having this very special critical point where there's a kind of a fractal structure of trees. And you go a bit higher than that, and suddenly you just have a big blob, which you can see from space, right? It's macroscopic. And then you keep adding more and more trees. Eventually, of course, it fills in. So in this case, when it's all, obviously in all of these examples, if you fill the whole thing in, toast, right? Every time it burns, every spark will burn it down. All right, so this is the case over here where we have two choices, and you see that the trees have been allowed to really fill in much more, put a lot more trees in before we've started to see the yield go down, right? What happens is you add more trees here, the yield starts to go down, right? You start to end up with less forest than you started with on average. There are a lot of blank spaces, empty points out here that are doing nothing. I mean, these are bad fire breaks, right? They are not helping. Yeah, so there's just a little hole here and the fire just goes around it. But there's a little one here and it actually gets all the way around there. So there is actually a real wall, a real fire break there. And there's a smaller one in here. It looks like anything that gets into this patch will actually burn all of that. So there's still a lot of randoms. Now, going up to n, so in this case 64, you've still got a couple of points that are a bit funny, but it's really, you've filled in more trees, a little more. I mean, there's still, most of the trees are there, really. You've filled in more, but you've got really clear fire breaks now. And going up to n squared, sort of cleans up that shape a little more, but I think this piece matches here, and this matches here, and so on. It's a little bit different, and this bigger piece matches here. So again, what do you think?
Capital D again here is like the number of times you run the fire experiment, so to speak.
Yeah, okay, so you put down, so in this case you put down, so say we're at this point. Now you get to randomly select from empty spaces, and you put down a tree. You run the world 1,000,000 times, however you want, see how it performs, and you do it again with another tree. You take that tree out and you do it again. The D equals 2 means you get to choose, you get two choices. Where to put a tree. So D equals 4 means you're at this state, let's add a tree, test it, and then we'll add another, we'll take that one out and we'll put it over here, test it, and then move our tree over here. So it's every time you're randomly selecting a place to put it.
So at each iteration, you select from D many random placements for the next tree.
Yep. Yeah. So n squared, this one, means that you tried every place, and then each time took the best case. Now, this doesn't mean you would get the optimal structure, right? Because ideally, you choose every possible configuration. This is a building thing. It doesn't. It's it's a greedy algorithm, if you like. It's not getting necessarily the ideal one. I mean, it's functionally totally fine, and it does what we want. Okay. So I mean, this is not necessarily the perfect one, if you analytically solved this. Yeah, but it's going to be very close. You can see that as you go from n to n squared, you don't get much more. There's a pretty big jump from 2 to n. So what do we think? Can I grasp this guy? This is this low entropy structure here. This is very random. This is very, you can see there's real structure in this thing. It's produced really, something that's really reacting or dependent on the underlying uncertainty of the environment, and it's very structured. So if the environment changes such that the lightning strikes are over here, or someone runs in here with a box of matches, then, right? And if that happens a lot, the environment changes such that fires are starting over here all the time, and this is really bad, because on average, this thing is burning down every time. So it'll be disappointing. So you have an uncertain environment, but it's stable, right? Stationary. It's an uncertainty that's stationary, right? You expect you expect the unexpected in the same way, right? But if you get a next level of uncertainty where the whole distribution moves around, then you're in a lot of trouble. So so there are two kinds of fragility. One is just you could just get a spark out here. I mean, this is really, these distributions are dying away very fast. You could just get one out here and then you're toast, right? It's going to be really sad. Or the whole environment could change as well. And that's a next level thing. And then depending on, and this is of course just this example, I mean, depending on how adaptable your system is, if it has any kind of ability to adapt and so on, then it can move to this new environment and not blow up. So very geometric. And then the next thing to see is that, yes, these are rare. This fire is going to burn all the time, right? These guys up here, you're going to get fires of these sizes all the time. These are less regular sometimes, not much at all. So we get this, you can't see it necessarily, but this parallel thing is going to pop out of it. All right, so these guys do well on average, but can just explode completely, right? So these ones over here, they kind of, most of the time things are burning, it's not good, but nothing horrific happens. This is horrific. This is your, 401k.
At what point did you choose to stop adding trees?
I don't know what that is anyway. What's that?
How did you choose when to stop adding trees?
Okay, yeah, so that should be robustness, fragility. All right, good. So that's on this slide, which we'll try to now comprehend. So this is the density that you've achieved by adding trees. Yeah, so you see, exactly. So you see when the thing rolls over. So actually it's a bit more than 0.5. So this is the random addition case, d equals 1. So once you can just keep adding trees using the same thing, right? I mean, you will eventually fill up the whole thing. So that, in all of these examples, once you've filled up the whole space, the yield is always 0, right? The whole thing is burning every time. So that has to happen. But to start with, because all these trees are isolated and not really connecting, it doesn't really matter which system you use, right? If you hit a tree, it's not going to connect to many others. So the fires are not so bad. So you typically, right, again, this is the density minus the fire size, right? So the density you have remains, right? So if you've got a quarter of the forest is filled and you burn a tree, it's basically still a quarter left, right? Or 2 trees or 3 trees, fair enough? But when you get to here, you burn a tree and it starts to get, many others. And there's a real drop off here, right? I mean, typically now you're expecting, right, to burn, more than half of what you have every time. So it's pretty bad. So that's the random addition one. Just making it 2 really changes the situation. You get, even though it's pretty messy looking, right? It's built some barriers in here that help the system out quite a lot, and design of n and n squared are right out there as well. Yeah, so, and the second one, what's up with the second one? Yeah, I mean, this is the we don't need to worry about this. This is the main story here. That's just more of the same. So is that fair enough? Yeah. So you stop, exactly, right? So the ones on the previous things correspond to this. So they have different densities, right? There's a much lower density. This is just, you were just able to, make a system that had at best had a much lower density of trees than these guys. So d equals n and d equals n squared are both there. So once you get to these optimal configurations for each one, then we're going to look at the so this is a cumulative probability of what we call the CCDF. This is event size here. These are pretty messy, 2 orders of magnitude. It's a very small system, so this is pretty borderline. But so this is d equals 1. Where is that guy? So that's pretty bad. Yeah. And d equals 2 is not so good either. D equals n is here. And it should follow the other one. Right. So these are somewhat, they're kind of parallel. These are pretty bad, actually. These ones, which look better, are fitting for the, it's the d equals n squared and, d equals n squared case. So this is the maximum design situation, right? So you're building the best ones you can every time using this process. And then the funny thing is, well, let's stop it at 0.1, 0.2, 0.3, 0.4, 0.5, and just look at that configuration, and then burn it, and burn it, and burn it, and look at the distribution. And in fact, the suggestion is you get power law size distributions for all of them, right? So this is just the density is 0.1, density is 0.9. So it's not just, the thing for the random case, it's just here where you get the power law distributions of sizes. Right? Below it, you get lots of little tiny ones. Above it, you always get a big one with lots of little tiny ones, right? Because there's a great big forest to burn every time. And it's really here, it's a critical point, it's a very special point at which you get it. The design, when it's highly designed, d equals n squared, at all along these densities, you're producing structures that have these, somewhat power law size distribution things. I mean, this is a huge range here, actually. So I don't know. This looks good. I don't know why those graphs aren't quite as good. So this would be a good game to reproduce all of these. I'm looking at someone who likes to code. Anyone who likes to code could do this. Okay, so this is going to be, this is actually real Star Wars again, but then we'll have some other stuff. Let's see if it explodes.
Use the Force, Luke.
Hilarious.
Let go.
This is just a break, people.
The Force is strong in this weapon.
Luke, trust me.
His computer's on. Luke, you switched off your targeting computer. What's wrong?
Nothing. I'm all right.
I lost our cue.
The Death Star has cleared the planet. The Death Star has cleared the planet.
Rebel base in range.
You may fire when ready.
Commence primary ignition.
Have you now? What?
Look out!
You're all clear, kid. Now let's blow this thing and go home.
Stand by.
So awesome.
Stand by.
Okay.
Great shot, kid. That was 1 in a million.
See?
Remember,
One in a
Force will
million.
be with you, always.
Okay, fantastic. So I'll tell you, I mean, I was 8, I think, when that came out. Hilarious. Right, so the narrative causality piece, the 1 in a million, very important, right? Yeah, we'll come back to that. Okay, so, and there'll be some more that connects to that particular piece there later on. So, I've said this, and I've just, the piece is just in here now. So if we're randomly adding trees, right, so robust yet fragile, right? Okay, all right, fine. If we're randomly adding trees, then this is equivalent to the classic, what's called percolation models in coming out of statistical physics. And I think that link should be to the kind of the great work on this. Yeah, Stauffer. It's actually 992. It's a really nice piece. That's really a lot of fun. Doesn't sound like it, but it is. So it's, academics' obsession with coffee, right? Percolation. Okay. So, it's the drug of academia. So randomly add trees, although some of them go for speed, right? Adish was on speed. Yeah, that works too. In the sense that, in fact, he went off it for a month and then decided, is this true? He went off it for a month and then said that mathematics had been hurt. Yes. Mathematics had suffered because of that. It said, couldn't tie his own shoelaces. He's the ideal mathematician, like no, just totally in the bubble, right? Couldn't butter his toast or whatever, Math, only math. Yeah. All right. If you're in the bubble, never leave the bubble, I guess is really the story. Okay, so we had this thing. So below this critical density, there are no big fires. Above it, very often we get this big burning of fires. So, it goes from this kind of scattered looking thing to something that has a big blob of trees in it that you can see, and there might be there'll be a bunch of little guys around it. So, this thing is blowing up all the time. But it's just at this, right, only at this critical density do you get this power law thing. So that's a really important aspect, right? When you try to go out to real systems and extrapolate from, or at least sort of conceptually take these kind of models and say, human society is percolation or whatever, or, the reason the power grid had a massive blackout is because it was on it's self-organized criticality, right? It's a bit of a difficult thing to think about. Okay, but it sounds great. Self-organized criticality sounds fantastic. So there are no features, of course, in that forest. As you saw, it's a mess. The hot forests, they're very structured. You get this power law distribution of tree clusters. Actually, even for, it's true. It's even, I guess the claim is it's for all kinds of rows, certainly above, I'm going to write that down. Certainly above the so-called critical density, which is only applies to percolation. So there's no specialness now of the density, right? You can make lots of different kinds of forests with this very silly mechanism for building forests that have these power law size distributions. The states are tolerant, right? They handle things pretty well. And you can handle it. So there are these 2 levels of uncertainty again, right? So it's pretty good with the uncertainty you have. You could still blow up even in that case. But if it's been characterized poorly or it changes, the uncertainty in the environment, then you're really asking for trouble. Yeah? You believe it? It's cool. So Doyle runs around telling everyone this is the truth, and it's pretty good. Okay, so these are examples being pulled out, and we could look at. So it's actually a more, a slightly improved way of fitting these things. But the idea is right. You're trying to minimize losses, and you've got some cost associated with resources you can use, which, as we saw with the forest, is really barriers, right? Geometric barriers. So that's a 2D situation. You're putting down 1D barriers. So if you have a 1D thing and maybe you're trying to break that up, you have 0-dimensional barriers. And 3D, you'd have 2D barriers. So there's a real dimensional story to this. So they have forest fires in here. What else do they have? There's a World Wide Web, lots of other things. Okay, so this is, again, fitting their stuff. Okay. So here's a way of, so we've got a model, we've just sort of walked through it. There's a way of, there are some rough ways of getting at it analytically, so we'll try to go through those. It's an optimization problem. As you can see, there's a constraint on the resources, so we should be able to construct something a bit like these Lagrange multiplier type situations we've had for Mandelbrot. So we have to measure failure size, right? So we have to be able to do that. And there's some, if we can correlate that with resource size, then something's going to come out of this. That's the story. We'll see how that works. So it's an inverse parallel relationship. So it's to do with the right. So this thing explodes and these things explode. The resources used are being used in a different way to prevent the fires here that they are here, and so there's some connection between the resources being allocated to these locations. Yeah. So we're not going to design as we have. I mean, analytically, we can't quite do that. I mean, it's a nice procedure to make a forest that does certain things. It's a good algorithm. But we want to do the same thing, but maybe we'll just do it with some optimization stories. So we want to minimize the cost. We have these sites, right? There'll be n sites, and there's a probability that the thing explodes, and then with probability that there's a, say in this case, like a forest fire of size y times y, right? So we have to, this is the average size of the cost. And there's a constraint with the resources, right? So each site has some resource associated with x sub I. That has to sum up to some constant. So this is our constraint. Right? We're trying to minimize the cost subject to this constraint. So it's the same kind of thing. Right. So let's see. So this is so with these percolation models, there are some sort of funny non-local things that you have to put in there sometimes. So I guess I could have kept that. But so we have some site I, right? Some site I here, and maybe it's got a tree in it, right? And then there are a bunch of trees around it, and so on. So you draw what you end up doing is you draw the boundary, right? Well, let's make it right. So maybe it's in an area of size I, right? Equals the area of trees. Connected in this nearest neighbor sense to I, to site I. Right, so you need to be able to measure this. So if we start burning here, what's the area? Fair enough? Yeah. So then this is where we start to put down our probability that site I gets hit. And the way this probability is a bit constructed is a funny thing. So, well, so it's the average probability of the fire at any site in the ith sites region, right? So it's a probability that you get anything starting in here. And it's the A sub I, as I said, is the area. So this is going to be, right? So the cost of the fire is going to be the probability of a spark in the ith region, the average probability, and then multiplied by A squared. Okay. The constraint, okay, so for this region, so if we look at this site, it's in some area A. And this is a bit of a funny thing again, but the typical, right, we imagine these areas aren't really weirdly shaped. So if there's some area A here, then the circumference or the perimeter should scale as A to the half, right? Pi r squared and 2 pi r. So there's that. So that's the cost for this guy. And then we're going to divide it across how much of the cost is associated with the nth site, or the site I. We have to divide it by the area of that whole thing. Right? All right, so all of these sites in here are part of this area. The cost to run that whole firewall around here scales like A to the half, and then we're going to divide its cost between all of these sites. So site I just has, right, so cost for site I is going to be proportional to 8 to the half divided by AI. Very naughty, messy things, okay. So you're assuming some kind of isometry. We'll talk about isometry and allometry later on, right? There isn't some funny, weird scaling. This is meters squared, this is going to be meters, so area to a half. And if we're in d dimensions, our half is going to be replaced by d minus 1 over d, right? So spheres, right, they're growing like cube power for volume, and the surface area is growing like a squared power. So in general, it's dq, it's to the, a length to the power of d and length to the power of d minus 1, so the 1 over 2 gets replaced by d minus 1 over d, if we're moving between volume and surface area. Okay, so then you can figure this out, and you get this relationship, right? So the probability that you want to choose your areas such that, and you already, this is something you're given, you want this relationship between the areas, right? So at the ith site, there's some probability of a spark, and that should be related to the area of that that burns as minus 2 plus 1 over d. So we're going to get a power law, and it depends on the dimension. So it's minus 5 halves for d equals 2. So we'll see if this works out. But everything's set up here, right? So the cost and the, okay, we're going to have this guy. We're going to this is robust yet fragile things to do with people's characters. So we'll have that. Okay. Does this sort of make sense? Sort of. Obviously, you're going to have to play around with it. Yeah, suffering. Yeah, very, very, very important. Yeah.
You're relating the size of the firewall. Well, the cost of the firewall per unit tree protected.
Yeah.
Okay, so that's what the A to the negative 1 is the per unit tree.
Yeah. So at the ith site, we want to associate the ith site with the cost. Yes, the cost of the area is going up as 8 to the half. Like the cost of protecting the area is going up as 8 to the half, which is not a bad return, right? Yeah, but then that's distributed among, yes.
So you'll have the lowest cost if you have enormous.
Yeah, so you get a good return actually, yeah. But that's dangerous, yeah.
Trying to figure out how quickly to draw the bound, like, so the fire's happening, you want to get out there.
So you have some sense of this uncertainty, right? I mean, that's characterized. You build the fire breaks and you maintain them, and you're not going to change them. So that design thing that we had before that ended up with a particular structure, the idea is from there you would actually just, keep going out and cutting things down to keep it nice and clear, maintaining it. So this is more of a maintenance one. Like you've been able to figure out from space or whatever, like this is where the sparks go. Right. Or that they're pyromaniacs. Yeah, right. So, there's you have some sense of it, so you build your, right. And if you've got it wrong, bears turn out to smoke in the woods, then you're in a lot of trouble. Yeah. Yeah, smoky, right. Okay, so it's something that you put these boundaries down, they're just there, the uncertainty is just there, these things are just ongoing. And if you lay them, you're always going to lose some stuff. That's right. This is a situation where things are going to go pop. But most of all, you want to have you want to build your little boundaries. You want to build small boundaries around the dangerous places, and let them go pop. But you've got to, like in Monsters Inc. when they put that thing on that guy, the one with the sock on him. No. You want those things around the parts that explode. Okay, so we'll watch this. I think this is...
So I threw the Senate at him. The whole Senate. True story.
Oh my God, that is so funny.
You made it come out of my nose.
Go for Papa Palpatine.
You have a collect call from...
I gotta take this. Hold on. Vader, how's my favorite Sith? Whoa. Just slow down. Huh? What do you mean they blew up the Death Star? Oh! Hey! What the hell is an aluminum falcon? Okay, so who's left? Are you me? Well, where are you? Wait a sec, you've been flying around for 2 weeks trying to get a signal? Oh, you must smell like feet wrapped in leathery, burnt bacon. Oh, I'm sorry. I thought my Dark Lord of the Sith could protect a small thermal exhaust port that's only 2 meters wide. That thing wasn't even fully paid off yet. Do you have any idea what this is going to do to my credit? Hang on, I got another call. What? I'm very busy right now. Oh, well, where are they going? Huh, all right, just get me a turkey club. Coleslaw, I guess. I'm not even gonna eat it. What are you getting? Yeah, see, I always order the wrong thing. No, I'll just stick with that. Okay, bye. What? Oh, cherry Coke. Thanks. Sorry about that. What? Oh, just rebuild it? Oh, that real f***ing original. And who's gonna give me a loan, jackhole? You? You got an ATM on that torso light bright? Now get your 7'2" asthmatic ass back here, or I'm gonna tell everyone what a whiny bitch you were about Padamame or Panda Bear or whatever the hell her name is. Oh, jeez, he's crying. Hey, come on, don't do that. Just, look, I'm just dealing with a lot of crap right now. Death Star blown up by a bunch of teenagers, I didn't mean to snap. Just get back here. Okay, bye. I love you too.
I'm sure you've all seen it, but anyway, it's thematically. Okay, so in fact, the next piece is to talk about self-organized criticality and then how these things compare with each other, and I think we can start that on Tuesday. All right. So highly optimized tolerance. It's a pretty great bit of thinking actually, and it's kind of a surprising. Went against a lot of what had been done before. Still being debated, as I said. There's some nice versions of this on networks. We could explore that as well. What's that? Oh, burning forest. Yeah, people love to burn forests down on computers. Yeah, that's a big thing. Yeah, for sure. Yeah, I love it. What's that?
It's a cool thing to do.
Yeah, they just think it's great. It's mathematicians who weren't picked for sports when they were kids. So they do violent things.
Is there
With
any,
math.
Soldier sonus going on with all the fires that are happening now, or is it?
It turns out to be a lot more complex than
Yeah. Well, so
random forest built from scratch.
yeah, that's true. So I don't think they're doing that, but the issue with that was stopping small fires, right? I mean, I think that's understood to be. So there's controlled burn off. Australia, of course, famously has terrible fires, and
The current issue is they don't have the money to maintain those fire breaks. That this model is like, oh, just maintain these fire breaks.
yeah,
And then their firefighting budget gets cut to a tenth of what it was,
and then there'll be a change in the outcome. Yeah, right. So I mean, it follows from the model. I mean, but also you don't need the model to figure that out, probably. But there was a long time where people would just stop any fire, right? That was sort of just a bad thing. But that meant you ended up getting a lot of stuff that was not being removed in a natural way, right? I know in Australia, I mean, there are forests that are they've evolved to love being burnt to bits, right? And then they germinate afterwards. Like they actually are really, right? So they want to be burnt. Anthropomorphizing, I shouldn't say that. Anyway, good. Escape.
Maybe like email or tweet at you to talk about project ideas.
Oh, yeah, projects. All right. Anytime. No, anytime. Absolutely, anytime.
I need to do some.
Yeah, anytime for projects, anytime. Yeah.
Yeah, I'm